Morning, everyone. How are we doing? Let's wait a few moments till everybody comes in. Let me try to adjust the camera while I'm here. I did very little. No, it's not doing anything. Jesus. Morning. Terrible. This is terrible. What have I done? Yeah, now it's bad, right? All right, I mean, we'll stop playing around with it. All right, how are we doing? Questions? Anybody? Let's get to work then. Today we're going to talk about prime numbers. But before we do so, let's take some time to introduce collections of numbers or sets that we're going to use throughout the course. So let's start with a definition. The natural numbers denoted by n, natural numbers, or sometimes referred to as the counting numbers, are exactly those numbers you use to count. So 1, 2, 3, and so on. Right, so natural numbers denoted by n, like this. This is what we're talking about. If you throw in a 0 there, yes, today is the first official class for Math 180. If we throw in 0, the natural numbers with 0, form the whole numbers. Denoted natural numbers with 0, right? Notation for the whole numbers. This is 0, 1, 2, 3, and so on. So natural numbers, whole numbers, if you take the whole numbers and their negatives, form the integers. Denoted with a z, right? So all of these and all their negatives. So -3, -2, -1, 0, 1, 2, and so on. These form the integers denoted by z. And I mean, you know that there are a lot of other sets. There are a lot of other collections, but for now, this will suffice to get us started. So that'll be enough for now. So natural numbers, whole numbers, and the integers. Let's start with a definition. So definition, a natural number n is said to be composite if n can be realized as the product of two natural numbers other than 1 and itself. Right, so we're starting with a definition of what it means to be a composite number. Say a few examples. 9, of course, you know 9 to be 3 times 3. So we have decomposed 9 as a product of two numbers that are not 1 and 9. 10 is 2 times 5. 10 is a composite number. But if you consider the number 17 and you try to split it up as a product of two numbers, the only way you can do that is 17 times 1. So 17 does not decompose as the product of two natural numbers other than 1 in itself. 17 is not composite. This leads us to the following definition. A natural number other than 1 is said to be prime if it is not composite. Now, the fact that one is singled out here might seem strange at first glance. And in fact, before the 50s, there wasn't a consensus as to whether one should be treated as prime or not. So if you pick up an old book, some books would treat one as a prime number, other books would not. So there'd be this confusion as to what's going on here. Now, however, that has been fixed, and the convention is that one is not a prime number, and we'll see exactly why that is momentarily. So our definition here of a prime number is a number that is not composite. Observe right, 22 is a composite number because you can break it up as the product of two numbers, 2 times 11, both of which are not 1 and 22. If we take this a step further, observe that 22 divided by 2 is 11. And similarly, 22 divided by 11 is 2. In the same way, 10, which was a composite number, 10 divided by 2 is 5, and 10 divided by 5 is 2. Where am I going with this? As opposed to 17, where that doesn't occur. The only numbers that divide 17 are 1 in itself, as opposed to composite numbers, where you might have other divisors. And this really leads us to perhaps the definition of a prime number that you had in mind. Right here we define it as something that wasn't a composite number. But if you remember back to high school and perhaps elementary school, you might have had a different definition of a prime number. And let's give it now. Definition: a natural number other than 1 is said to be prime if and only if it is only divisible by 1 and itself. Right, so here 10 was divisible by 2 and 5, so 10 is not a prime number. 22 was divisible by 2 and 11, so 22 is not a prime number. 17, however, was only divisible by 1 and 17, so 17 is a prime. And again, this is perhaps the definition you remember, let me take a moment to discuss the divisibility condition here. When we say divisible, we of course mean that the quotient should be in the natural numbers, right? I mean, you're thinking to yourself, 3 is divisible by 2, right? Because when you divide 3 by 2, you get 1.5, but 1.5 is not a natural number. So in this context, we would say that 3 is not divisible by 2 because we want the quotient to be a natural number itself. Right here, this whole discussion of prime numbers is restricted to the natural numbers, at least for now. Let's list the first few natural numbers and ask ourselves, are these prime or composite? And we're going to leave one aside for obvious reasons, right? Because by definition, 1 is not a prime number. So what about 2? Is 2 a prime number or is it composite? Can we decompose 2 as a product of numbers different from 1 and 2? Or similarly, what are the numbers that divide 2? It's only 1 in itself. It's only 1 and 2, so 2 is prime. 2 is a prime number. What about 3? The only numbers that divide 3 are again 1 and 3. 3 is prime. 4, however, you know that you can factor 4. 4 is really 2 times 2. So this is a composite number. 5? 5 is prime. 6? Well, 6 is 2 times 3, so composite. And so on. This leads us to an interesting way to list all the prime numbers known as the sieve of Eratosthenes. Here, you list all the natural numbers. So let's do that. 2, 3, 4, 5, 6, 7, 8, 9. Where do I want 10? Let's say 10 here. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And so on, right? I'm going to stop now. And what does the sieve tell us? Smallest number is prime. So this is a prime number. Now we remove all multiples of this number. So 2 times 2, 2 times 3, 2 times 4, 2 times 5. These are not going to be prime numbers, right? Because they're composite. It's 2 times something. 2 times 6, 2 times 7, 8, 9, 10, and so on and so on. So all of these things I'm crossing out are not prime numbers for obvious reasons. Repeat. Smallest number is prime. 3 is the next smallest number. Remove multiples of 3. 3 times 2. 3 times 3. 12, 15, 18, 21, 24, 27, 30, 33, 36, 39, 42, and so on and so on. Next smallest number is prime. Remove multiples of 5. 5, 10, 15, 20, 25, 30, 35, 40, and so on and so on. The next smallest number is prime. Remove multiples of 7, so 14, 21, 28, 35, 42. Next smallest number is prime. Right? I mean, all of these have been crossed out. 11 remains. So we'll take away multiples of 11, 22, 33, 44, and so on and so on. Next smallest is prime, and so on and so on. I think you see where this is headed, right? This is a nice way to list all the primes, known as the sieve of Eratosthenes. How are we doing here? Questions? Now, I mean, it is possible to use the sieve to get all the primes. Of course, it's going to take forever. And in fact, here's a question. Is 97 a prime number? Does this have any uses apart from just listing the primes? Well, I mean, let's ask ourselves this. Is 97 a prime number? It's not immediately clear. Maybe it is, maybe it isn't. We could use the sieve of Eratosthenes to determine, right? You can continue in this fashion, crossing out multiples of 13, so 26, 39, and so on. And then 17 is prime. And you continue on until one of two things happens. Either 97 has been crossed out, or it hasn't, and then you circle it as a prime. So, I mean, you understand that this is going to be quite a long process, but at least it's going to give you the answer. The question arises, is there a faster way? And the answer is yes. I claim that we don't need to use a sieve of Radhasteins to determine if 97 is prime, I claim that since, so here's my claim, we only need to check whether 97 is divisible by 2, 3, 4, 5, all the way to 9. We only need to check whether 97 is divisible by these few numbers. Why is that? Consider the following theorem. Suppose a natural number is composite. Right, so suppose that then there exists, right, what does it mean to be composite? It means that it is the product of two numbers other than one in itself. So there exists two numbers, A and B, two natural numbers, where n is the product AB. I've jumped the gun here. This is not how I wanted to state the theorem. Let me start over. Sorry about that. Suppose a natural number is composite. Then there exists a factor less than or equal to root n. Let me now restate this with those actual factors AB. All right, so that's the real statement I wanted to give. If a number is composite, then there has to be a factor less than root n. That is, if n is equal to AB, where A and B are natural numbers, and A is the smaller of the two, and A is not equal to 1, then A has to be less than or equal to root n. And let's prove that. Because the proof is trivial. It's a one-line proof. Right, so we're saying if you have two factors, one of them has to be less than or equal to root n. Suppose not. Right, so it's a proof by contradiction. Suppose not, then A has to, right? I mean, what's the, here our conclusion is that A has to be less than or equal to root n. So if it's not true, then A has to be bigger than root n. But B is bigger than or equal to A. So B is also bigger than root n. And AB must therefore be bigger than root n times root n, which is equal to n. But AB is n. So n is bigger than n, which is a contradiction. There it is. Right? If both factors are bigger than root n, then their product has to be bigger than n. Contradiction. So what does this imply as far as we're concerned? What does that imply? This implies that in order to check whether to check whether 97 is prime, there should be a prime or not. If it's composite, there's going to have to be a factor less than or equal to square root of 97. So square root of 97 square root of 97, well, that's less than square root of 100, which is 10. So this is going to be 9 point something something. So is 97 prime? All we need to do, if 97 is not prime, there has to be a factor less than or equal to 9. So you only need to check whether 2, 3, 4, 5, 6, 7, 8, or 9 divides 97. If none of these numbers divide 97, then 97 is prime. If one of these numbers divides 97, then it is not prime. And that's it. So you can do that with a calculator or, pen and paper. It's all good. Let's just do it quickly to answer that question, because we've asked that question for a while. We still don't have the answer. So first of all, 2 does not divide 97, right? Because 97 is not even. So 2 doesn't divide. What about 3? If we do 3 into 97, 3 times 3 is 9, leaving you with a 7, and then it doesn't work, so that's out. 4 is not going to divide, again, because 97 is not even. 5, it's easy to see that 95, right? So now you're left with 2, it's not going to work. 6 is even, so that's not going to work. 7 is 97 divisible by 7. Not clear. 27. 3 times 7 is 21. 4 times 7 is 28. It doesn't work. We've got a remainder of 6. 8 is not going to divide because this is not an even number. And finally, 9. Well, I mean, you see that 9 goes into 9 once, but then you're left with a 7. So no good. None of these numbers divides 97. 97 is prime. Now, if you take a step back, you know, we considered all of these numbers, but in fact, we did not need to. We did not need to consider all of these. And let's think about why that is. Suppose 2 did not divide 97. Well, in fact, it doesn't, right? It's impossible that 4 is going to divide because 4 is actually 2 times 2. So if 4 divided 97, then 2 would have been a factor as well. So we don't need to consider 4. Same with 6, right? 6 is 2 times 3. So if 2 or 3 were factors, right? I mean, if 6 is a factor of 97, then 2 and 3 would automatically have been factors as well. And same for 8. 8 is 2 times 4. And 9 is 3 times 3. So we did not need to consider these composite numbers less than or equal to root 97. In other words, we only need to consider the prime numbers less than root 97. And this is true. This is always true. Let's make this clear as the theorem. Theorem. If a natural number n is composite, there exists a prime factor less than or equal to root n. So you don't need to test all numbers less than or equal to root n. You only need to test the prime numbers less than or equal to root n. Marley is asking if we'll be graphing in this course. I may be graphing a bit, but you will not need to. No. Let's take an example to illustrate this. Here's the question, is 437 prime? I mean, it's not clear. Maybe it is, maybe it isn't. If you had a calculator, you can check that the square root of 437 is 20 point something something. So is 437 prime? All we need to check is whether 437 is divisible. By the prime numbers less than 20, less than or equal to 20. What are they? 2, 3, 5, 7. Next prime is? What's the next prime after 7? 11, thank you. Followed by 13. After 13, 14 is not prime. 15 is 3 times 5. 16 is 2 times 8. 17 is prime. 18 is 9 times 2. 19 is prime. And 20, of course, is not prime. There it is. So all we need to check is whether 437 is divisible by each of these numbers. It's a little bit of work. If you've got a calculator, it's very quick. Somebody with a calculator, check. Is it divisible? Is 437 divisible by any of these numbers? Does anybody have it? Somebody working that out? Divisible by 19? 437 is 19 times? Times what? 19 times 23, thank you. I'll leave you to check that. But really all you had to do was verify whether these were a factor or not. If one of them is a factor, we're good. If it isn't, then 437 would have been prime. Let's take another example. How are we doing here? Thank you. Consider this. 252. Is 252 prime? Clearly it is not, right, Matthew? Thank you. It's obviously divisible by 2. Why don't we divide by 2? So this is 2 times 126. I think that's pretty clear. Are we allowed calculators in this class? Well, here's the thing, right? Short answer, we would have allowed non-graphing, non-programmable calculators if this was a regular in-person class. Of course, everything's on the internet now, so there's no way of checking. So calculators will be allowed. It's going to be open book, open internet, You can use pretty much anything you want, except for discussion with other people. Right, so 252, not prime, obviously. And we have factored it in this way. It's 2 times 126. And now we can ask the same question. Are these factors prime? Are these factors prime? Well, 2 is prime, absolutely. Very nice. What about 126? 126 is not prime, right? I mean, I think it's clear that it's an even number, so it's divisible by 2. Let's divide by 2 again. This is going to be 2 times 63. And repeat, are these factors prime? Well, 2 again is prime, so we'll leave it. 63, as suggested, is divisible by 3. This is 3 times 21. And repeat, are these factors prime? Well, 3 is, but 21 is not. 21 is 3 times 7. And repeat, are these factors prime? Now the answer is yes. So we can rewrite this 2 times 2, or 2 squared, 3 times 3, or 2 of those 3's, and a 7. And what have we done here? We have taken this big number, 252, and we have decomposed it as a product of prime numbers. This motivates the following theorem. If you think about it, this can always be done. Right? You can always do that. You take a number, and you can always decompose it. Well, I mean, first of all, if the number is prime, you're done. If the number is not prime, you can factor it, and then repeat on each of the factors. So this leads us to the following theorem, known as the fundamental theorem of arithmetic. Which says that every integer other than 0 and plus or minus 1 is a unique product of primes. Right? So every integer other than 0 plus or minus 1 is a unique product of primes. Right? In other words, this idea can always be repeated. And this fundamental theorem of arithmetic really is the reason why 1 is no longer considered a prime number. Right? Because if you take 21, which is 3 times 7, right? This unique product of primes. Well, if 1 was there, then you could rewrite it as 1 times 3 times 7. And you could also rewrite it as 1 squared times 3 times 7, and so on. So this decomposition into a product of primes would no longer be unique. So that took care of the 1 as a possible prime number, and that's why now the convention is that 1 is not prime. Let's take an example of this. Even negative integers are unique products of primes, right? Because as you pointed out, now we've suddenly moved on to integers when we were always restricting our attention to natural numbers. So what happens with integers? Suppose you have negative 10. Forget the negative. Just take it out. This is negative 10. This 10 is a natural number. So this 10 is a unique product of primes, namely 2 times 5, and that's it. You have a negative outside, not an issue. So this generalizes the idea of decomposition of primes in the natural numbers, immediately generalizes to integers if you factor out a negative, and that's it. Let's take an example. Question is asking us to decompose 5,544 into a unique product of primes as guaranteed by the fundamental theorem of arithmetic. All right, so you take 5544 and you realize that it's even. So we can of course divide this by 2. If you have a calculator, right? Somebody's asking, what if we rewrote this as negative 1 cubed times 2 times 5? Now we lose the uniqueness, right? That's what you're thinking. Absolutely. However, negative 1 is not going to be considered a prime. So there's really no point in doing that, right? It's the prime numbers that we're interested in. So even though nothing is wrong with that, it still doesn't really contradict, because very much like 1 was not a prime number, neither is negative 1. Somebody is telling us that this is 2 times 2772. Very good. 2 being a prime number, we're good with that. Here, this is even again, so we can factor out another 2 from there. This is divisible by 2, and what do we get? 1, 8. No. 1, 3. 86. 1386. Marley, why does that get rid of the uniqueness? It doesn't, right? Because the -1 here is not prime. We're not considering that as a prime number. So we do not lose the uniqueness. We can divide by 2 again, absolutely. So 2 times 2 times 2. What do we have? 6, 9, 3. Is that correct? 693, thank you. Thank you. And 693, somebody is telling us that it's divisible by 11, perhaps. Immediately I would have said a 3, right? Because 3 is going to divide every digit here. So, well, I mean, first let me do some shorthand here. 2 times 2 times 2, this is 2 cubed. And here I think we can factor out a 3. This is 231. Thank you. 2 times 231. 3 times 231. And now, I mean, the question arises, is 231 prime or not? It's not clear. Although somebody did at one point mention that this was divisible by 11, so this gives you a hint as to whether or not it's prime, but square root of 231, what is that? I've worked that out, 15.19 something something. So you could test whether it's prime or not by looking at the prime factors from 2 to 13. But as Julie is suggesting, 231 is 3 times 7 times 11. So there it is. But if you weren't sure, and if you didn't see it, you could test whether it was prime or not by this trick, right? Because it could have been prime, and that would have been the end of it, but it isn't. So this is 2 cubed times 3. 231 is 3 times 7 times 11. So in other words, this is 2 cubed, 3 squared, 7 times 11. And we have decomposed 5,544 into a unique product of primes. How are we doing? Questions here? Anyone? So this is actually all I had for today. So I realize we still have some time, but that's all the material I had prepared. So that'll be it then. We'll pick this up again on Monday. I won't open up the web work yet because the first web work is going to be on prime numbers, and we're going to do more on Monday, but I'll open it up after Monday's class. So you guys have a good weekend, and I'll see you Monday. Valerie's asking, how do we access web work? Through the link on my courses. It's the only way you can access web work from now on. So there's an assignment 0 up already. Have a look at it if you haven't seen it, especially if you have never worked with the WebWorks system before. It's a tutorial on the WebWorks system. It's not for marks. So have a look at it. WebWorks 0 is not graded. That's right. Yeah. Very good. So thank you for coming, and I will see you on Monday. Have a good one.